Sorry, yeah, let me start. So, yeah, thank you for inviting me to this nice workshop. So I was asked to talk about this PR paper. I wrote the paper with Komatsu about the measurement, a new measurement of the cosmic birefringence. However, after that, there are some updates in the measurement of cosmic birefringence with us and as a group. So I will talk all of them. Let me introduce. So just now, the universe energy budget is dominated by two dark components, dark energy and dark matter. Parity violation may hold the key to understanding their nature. For example, the action like particles. We know that the weak interaction violates parity already. So phi should the laws of physics governing the universe conserve parity. The key is the cosmic birefringence. It's like the universe filled with a birefringent material, like a sapphire crystal. If the universe is filled with a Schur scalar field phi, one example is action like field coupled to the electromagnetic tensor via a Chern-Simons coupling. This is the additional term in Lagrangian density. This is the coupling constant G, and phi is the Schur scalar field and electromagnetic tensor, and it's zero. So phi is the Schur scalar, so phi is odd, and so F mu 2 term is parity odd. But in total, this term is parity even. So we can see parity odd effect in electromagnetic effects. So if photons travel the birefringent material, the linear polarization plane is rotated by angle beta. Beta is related to G phi gamma over 2 times the difference of field values at the observer point and emission point. So we can measure the effect of parity violation with the rotation angle beta. So we know that the cosmic microwave background CMB has a linear polarization. This black line shows the linear polarization pattern observed by ESA's Planck satellite. CMB was emitted 13.8 billion years ago at the last scattering surface. This is the picture of the CMB. And we know that the initial beta, rotation angle beta, is 0 in the standard cosmology because of parity conservation. So we can measure if we measure the non-zero beta in the CMB polarization signal, we can test our universe is parity even or not. So okay. So in the case of action like particles, so yeah, maybe some theories. Just a moment. We'd like to know what is the target which we can target dark energy or dark matter with the measurement of cosmic microwave background. So this is a sensitivity to the action like particles in the plane of coupling G against the mass of the action like particle. At this minimum point, the most sensitive point corresponds to the mass is equal to present Hubble. So the mass is 10 to the minus 33 electron volt or so. So if the mass is greater than the mass present Hubble, the actionary particle can be dark energy. It can explain dark energy. However, if the mass becomes smaller, it loses the sensitivity because the oscillation of pseudo-scalar field becomes smaller, and the field value difference between observer and the emission point becomes smaller. So we lose the sensitivity. And if mass becomes higher than present couple, it can be part of dark matter. Because if this small mass dark matter disturbs the structure formation, so it cannot be all the dark matter component. So it can be part of dark matter. And if mass becomes larger, it loses the sensitivity because of the damping effect by the thickness of last scattering surface. So it starts to oscillate during the last scattering era. For the details of action-like particles, please see Marsh and Ferreira review papers. So next, so we know that CMB has a linear polarization pattern, E and B modes, which is a decomposition of linear polarization in polarization. And in real space, we measure the linear polarization with two orthogonal Stokes parameters, Q and U. We transform them with a Fourier transformation and measure this E and B mode in Fourier space. E mode is a polarization direction. E mode has a polarization direction parallel or perpendicular to the wave number vector. B mode is 45-degree tilted or minus 45-degree tilted against the wave number vector. So how are they transformed under the parity flip to see the parity violation effect? Under the parity flip, horizontal E mode transformed to horizontal and perpendicular to perpendicular. And so the E mode is parity even. B mode 45-degree tilted is transformed to minus 45 to 45. So B mode is parity odd. However, in the real measurement, to extract the information of our universe, we use two-point correlation function. So maybe you know some E mode. It means the E mode autocorrelation. And B mode is the B mode power spectrum means the B mode autocorrelation. Because their autocorrelation parity even, they are parity even. And the other parity even components are TE cross correlation. This T is a temperature anisotropy. So this is only a scalar variable, so parity even. So TE and ET cross correlation is parity even. The others, for example, TB and EB are not invariant under the parity. So we can use these variables to probe parity-violating physics. And in this talk, we concentrate on the EB cross correlation. So how can we measure the beta with the EB cross correlation? The cosmic birefringence convert E and B. And at the emission point, this is the E and B mode emitted. And with rotation beta, the E and B modes are mixed with this rotation matrix. They are rotated by 2 beta, and we observe the rotated E and B mode. From these coefficients, we can construct the power spectra, EB power spectra. And observed EB power spectra is related to 1/2 times CFEE minus CFBB. These CFEE minus CFBB are the power spectra as emission, and times sine for beta. So there, the E mode minus B mode is rotated by for beta. And the last term shows the intrinsic CMB mode EB cross correlation term. This should vanish at the last surface in standard cosmology. So if we fit the observed EB with E minus EB, we can determine beta. here is update. So we found a new relationship in the observed EV. So from the same equation, with some complicated calculation, we derive a new equation. Observed EV is related to observed EE minus observed EV. So difference is observed. They are observed variable. And the quotient is the tangent for beta. So difference is this term, and the EE minus EV became to observed variable. So we don't need a model to estimate the beta. Only the observed EE, BB, we can determine beta. So this is a key to measure the cosmic birefringence. So yeah, we can determine cosmic birefringence angle beta with this equation. However, there is the biggest problem. So that is the miscalibration of detectors. We would like to measure the birefringence angle beta. However, if there is a rotation of polarimeter alpha, let's assume there is a rotation of the detector. We assume a polarimeter to sense this direction. We assume. However, if there is a miscalibration, they are rotated by this angle alpha. If we don't know the rotation angle alpha, we can only measure the sum of alpha and beta. So we have to break the degeneracy to determine beta. We have to calibrate the detectors. This is some table of the past measurement. So in the past measurement, systematic errors on alpha limited the measurement. For example, the first measurement of the cosmic birefringence is here. However, they did not calibrate detectors, so there is no systematic alpha on beta. Sorry. About the Planck result, they reported the best fit value to 0.1, start uncertainty is 0.05, and the systematic uncertainty is 0.28. This is comparable to the best fit value, so they reported the value is consistent with 0. So anyway, so this large systematic uncertainty limits the measurement of cosmic birefringence beta. If this value is the case. So to reduce the systematic uncertainty, we came up with the idea. So to use the polarized galactic foreground emission as a calibrator. This is the distribution of the foreground emission. So polarized dust emission within our Milky Way. So because the emission, they are emitted right there, very close to us, so it would not be affected by the cosmic birefringence. The effect is extremely small compared to the long distance of the CMB. So we can use the foreground to calibrate our detectors. And so, yeah, miscalibration of the polarization angle alpha rotates both the foreground and CMB. But cosmic birefringence beta only affects only the CMB. For example, in the case of E mode, E mode observed is composed from the foreground EP rotated by only alpha, and CMB E mode rotated both by alpha and beta. In the case of B mode, that is similar. Observed B mode is from foreground B mode rotated by alpha, and CMB B mode rotated by both alpha and beta. From them, we derived a new equation. Observed EV can be related to the first term shows the alpha and the observed variable, and the second term shows the birefringence and beta, and the CMB E mode minus CMB B mode. So we need to assume some model. And And the last two terms show the intrinsic foreground EV cross correlation term and CB EV cross correlation. As I said, we can neglect this term. However, we cannot neglect this term. So I will revisit this term afterwards. Anyway, if we neglect these two terms, okay, so we can determine both alpha and beta. We constructed the likelihood with the equation to determine the alpha and beta simultaneously. The numerator is the left-hand side minus the right-hand side, and denominator there is a correspondent variance. For analyzing the Planck data, we use a multi-frequency likelihood developed in Minami and 2028. So the likelihood was modified. And we first validate the algorithm using simulated data. So we assume the future satellite mission light bird and test our algorithm. So in semi-dominated channel, these are the determination of these are contour of the determination in the alpha beta plane. In semi-dominated channel, uncertainty alpha plus beta is very determined. Uncertainty alpha plus beta is very small because still this is the semi-dominated channel. However, the uncertainty on alpha is large because the foreground signal is small. So the uncertainty on beta is large. On the contrary, in the gas foreground dominated channel, uncertainty on alpha is small. However, the uncertainty on alpha plus beta is very large. So we cannot determine beta well. In mid-frequency channel, so uncertainty on alpha plus beta is small and uncertainty on alpha is small. So we can determine beta well using both theory and programs. So next we applied the method to Planck data. So we use Planck high-frequency instrument data from 4 frequency bands, 100, 153, 217, and 353 gigahertz. And here is the result. So we find the best fit beta to be 0.35 plus minus 0.14 statistical uncertainty. So it means the significance is 2.46. And because there are 4 frequency bands, we have 4 different alpha. So these 3 alphas are consistent with 0 in the statistical uncertainty. And this alpha 100 is consistent with 0, including the systematic uncertainty of Planck calibration. So all the alphas are consistent with 0. But however, here you may think this negative alpha 100 would push up the measured beta to positive. However, even though the removing alpha 100 did not change the measurement value of beta, because 100 gigahertz band is very noisy. And this beta 0.35 is consistent with the Planck result estimate value. And these are the observed EV power spectrum black dots, and the blue is fitted CMB power spectrum, and red is observed power spectrum. So if there is a cosmic birefringence, you may see the black dots synchronized with the blue dots. Can you see? So maybe it is very noisy, so you can see. So afterwards, after our publication, so SQ and Komatsu released archived paper. That includes from HFI, LFI double map data. And they show the stacked EV power spectrum. So the noise level is very small, and you might see the black dots seem to synchronize to this blue cosmic birefringence power spectrum. Then, yeah, they reported, including WMAP data, the resulting beta is 0.34 plus minus 0.09. So the significance increases to 3.6 sigma. So what does it mean for your models of dark matter and energy? So let me skip this thing. So as I introduced, the beta is related to a coupling constant and the difference of field values. So we can only set the limit with the product of coupling constant to and the difference of field values. The value is 1.2 plus minus 0.3 times 6 minus 2 radian. So you can directly put this value to your models. And yeah, at first, let me talk about the intrinsic foreground EV. If that exists, our method interprets it as a miscalibration angle alpha. In that case, the alpha is modified to alpha plus gamma, where gamma is a parameter of the intrinsic EV. The sign of gamma is the same as the sign of the foreground EV. So that we can determine alpha plus gamma with foreground, alpha plus beta with sigma. So using the subtraction, we can only determine beta minus gamma to be 0.34 plus minus 0.09. However, there is evidence for the dust-induced PE to be positive, PB to positive, then we would expect EV foreground to positive. In that case, gamma is positive. If so, we can give a lower bound on beta to be 0.34 plus minus 0.09. And in the latest paper, we included the foreground model. And without foreground model, we determined the beta to 0.3 plus minus 0.1. However, including foreground model, the resulted beta is 0.36 plus minus 0.11. So anyway, so without or with foreground model, we can have the similar best fit value. And let me conclude. So we find the heat of the parity-violating physics in the CMB polarization. Now the angle beta is 0.34 plus minus 0.09. Higher statistical significance is needed to confirm this signal. We should be possible to test the signal is true or only listening. If confirmed, it would have important implications for the dark matter or energy. That's all.
I have two questions. First, do you have like sense of how these numbers will improve in the future CMB experiments, like CMB stage 4 and so on?
Yes. Maybe if ground-based measurement includes a high frequency band and see the galactic plane, that can use this method and can increase the sensitivity.
So do you have like rough sense how well, for example, for delta and effective, we kind of have a number, right, from 0.5 or so down to the 0.02 or so. So we know how well it can be improved. Do you have sense like how well CMB protocol can improve this number for beta?
No, I'm not sure because I don't know the sensitivity. However, if we increase the future satellite mission lightweight, that can increase the sensitivity by 5 signals.
Okay, good. So then if I take this as like true value, meaning let's say I believe this number and that there is actually actual CMB violating physics, you put a number in terms of like theory parameters, coupling times difference of the phi.
Yes.
Roughly, so this is in terms of different unit. This corresponds roughly do you have sense what is the now Topological scale associated with these numbers? So what kind of theory parameter in terms of like the U1 PQ violating scale give rise to this axiom physics?
I'm not sure. So
yeah, so the G is 1 over F roughly. Yes.
Yes.
Yeah. I was wondering if you have a sense. Oh, okay. There we go.
So if we find the cosmic birefringence with the sensitivity level of this is the case, the angle 0.3. So and the sensitivity with light path. However, the coupling can be 10 to minus 20 GBE.
I see. Okay, that helps. Okay, thanks.
This is for which beta? What value of beta?
Maybe this assumes the 0.3 degree.
Yes, sorry, at some point I lost track of this in the community. There's ACT-Qual and all these other CMB emissions. What do you know if they have any results on this, and what do they think about this non-zero beta? I mean, as opposed to just Planck or practical beta.
Yeah, ACT reported the angle is consistent with zero in their within their uncertainty. However, they assume an optical model. So they, to tell the truth, they did not calibrate the rotation of detectors.
So they did not include alpha, is that what you're saying?
So they assume that their optical model is perfect. In that case, the uncertainty of alpha, they say maybe 0.09 degree or so. So, and they measure the beta is 0.07 or so. So that is consistent with zero.
Can you apply your method to the data?
This method?
Yeah.
No. Just a moment. I will show some slide. So to tell the truth, the past ground measurement concentrate on the measurement of CMB mode. So they don't want to see the sky area where foreground is dominant. However, in this method, we need the foreground to calibrate our detector. So yeah, ACT DR4 map, they only see this small sky area, which is far away from the object. So they cannot use our method. And also, yeah, they observe the 95 gigahertz region where the foreground is very low.
Where the foreground is very
So the key is foreground. So we need the high frequency region and maybe close to reactive region to use our method.
Okay, thank you.
Yeah, if we believe the beta is not zero, does that really mean sign for the limit or sometimes sign for the example, primordial magnet. You talk about that, some kind of
So I don't think that is primordial magnetic field. So in the case of magnetic field, the beta should follow the frequency, some frequency dependence. Then skewed measure the we can try to measure the skewed 2022. They try to measure the frequency dependent cosmic birefringence, but the spectral index is consistent with zero, so the beta is flat in the frequency space. So I don't think that is magnetic field. And someone may think, yeah, this can be from the weak interaction. Some interaction with neutrino perhaps can create beta. However, with some theoretical paper that was excluded. So I think this is for the physics, or perhaps some unknown system.
So did you say that ACT was 0.09 plus minus 0.09?
Yeah, I don't know.
So is that intention, like the maximum beta that they allow is 0.18. Is that in tension with the data that you mentioned?
Yeah, there is a tension.
Yeah, Just about the answer to some of the questions. So your bound is on the product of the coupling and the field value, which is independent of that. So some other inputs have to go into that plot. You picked out a particular range of big gamma. Okay, what does it?
I couldn't hear.
Yeah, so your bound.
Well,
Your bound is on the product of the coupling and the field value.
yes,
Which is not different. In other words, it depends on the angle data of the axon, but not on the actual problem. But in response to some of those questions, you showed us a plot that referred some value of coupling. So there must be some other physics behind that. I'm wondering what might.
so just a moment. With simple action like particle case, the beta is related to the product of coupling and value, and
Yeah, so from that alone, you don't get for number of key gamma. It's only experience product.
yeah, we don't know.
So but then you showed us a plot with some values of G by gamma. So I'm wondering what other physics.
Yeah. So so in this paper we discussed we calculate the time propagation of field value, and so this is related to the difference of field value. So if the difference of field value becomes smaller, they lose the sensitivity.
Yeah, so that's thank you for very good talk.